You can turn the railroad cars upside down without disconnecting. So you come into this special machine, they do it 2 at a time. So 2 of these railroad cars flip upside down, still connected to the rest of the train. Dump the coal out, flip them back, and they do that as fast as they can all day long. That's how fast they consume coal at the power plants. So hundreds of tons, sometimes thousands of tons, hundreds of tons per hour, thousands of tons per day. So that's a big operation. And so we will go through. We're going to step through several things. We're going to start with the coal. What happens to the coal here? I meant to bring some coal with me, but so coal starts out. You've seen a picture of it, so I'm curious. How many people have actually touched a piece of coal? Most of it. So most of the coal you see is a rock, typical rock shape, chemical rock. And so that's the way coal gets shipped. So these red lines are going to be the coal. It comes out, and actually, if you've seen it on a railroad car, it gets crushed down to not rock throwing size, but down to smaller size. They don't make it any smaller than that because it would all blow out of the railroad cars if they did, and probably more significantly, it would catch fire. So occasionally they have that problem in railroad cars now. So they fill these cars up. By the way, one railroad car holds about 100 tons of coal. This is a measure. Depends on the type of coal. And so if you get 100 railroad cars together, 100 railroad cars, 100 tons of coal each is what they call a unit train. And when you order coal at a power plant, you order unit trains of coal. So you say, so 100 times 100, that's 10,000 tons of coal that you order at a time. It's a lot of coal. And they'll go through a couple of unit trains in a day. So that's a lot of coal that you're burning. So the coal comes out in that kind of crushed coal form, which is kind of like the size of gravel, a little bit bigger than gravel, and it gets loaded up into a hopper where the amount of coal, typically you have about an 8-hour supply of coal you put into this silo or into this hopper. It just piles up in there. But coal at that size is way too big to burn very efficiently. So as you burn it, it comes out the bottom of this hopper and it goes through this coal mill. And there's typically 4 or 5, sometimes 6 of these at the plant. So remember, this is a person, so the person isn't even as big as the foundation of this mill, but the coal comes down there and it gets pulverized to about the consistency of household flour. So, so specifically, it's reduced to about average size of about 45 to 50 microns, a top size of about 70 microns. So the biggest coal particles are roughly the diameter of a human hair, and most of them are quite a bit smaller than that. So you pulverize them in this pulverizer, and then so there's, in this case, there's 5 pulverizers. So you have coal going into each one of these 5 pulverizers. And then it gets transported pneumatically through these pipes. So air blows through here and picks up the coal and carries it in air to the burner. So it's important that we get this technology down. So this thing is called a boiler. This is a power plant. This is a boiler. A lot of people get boilers and burners mixed up. So in a typical boiler, there are rows of burners, and there might be anywhere from 15 to 30 or 40 burners on a boiler. So we'll look at pictures of burners in just a minute, but you have a whole bunch of places along the side of this big boiler where you're injecting coal and air and forms a flame. Each one of those is called a burner. So the air that carries the coal into the boiler goes through a burner. And so remember, just keep this guy in mind, and you form a fireball that's about this big. So that's like twice the height of the Clyde building. So you have a flame, just a big belching flame that's twice the height of this building. So that's a big operation, and that gets pretty intense. It's pretty fascinating to watch what happens here. So the coal gets blown into the burner, forms, typically you stabilize the flame right in front of this, and then the flame kind of comes up here and mixes with all the flames from all the other burners and forms this big fireball in the middle of the system. The coal burns out. It takes, so the total amount of time from here to the point where the coal is burned out is about 2 seconds. All right, so it goes, zips through this pulverizer, gets pulverized. It probably spends more than 2 seconds in the pulverizer. So It's about, but it's less than 2 seconds from here to there, and particle gets injected into this furnace and has a lifetime of typically about 0.9 to 1.2 seconds in the boiler.
Do we have to force air into the boiler to get to burn that much?
So we're going to go through the air next. We'll go through the coal, and then we'll talk about it. So there's some air transporting coal here, but that's just transport air. So most of the air is not. The great majority of the air comes in a different system. So the coal starts here, gets up to here, and it's completely burned out. And the flame is so intense. Remember we talked about these 2,000 and some degree temperatures that there's actually nothing that you can put in this fireball that would have any lifetime of any significance. So what you're trying to do is get heat out of this flame, but you can't put heat exchangers and stuff like that into the flame because it would just destroy them. And so the walls of this boiler are made, they have water going through pipes in these walls, and they're absorbing the heat almost entirely by radiation from that fireball, at least up until this point of the flame. So you go from something like 2,000 degrees Celsius here to at the top of the boiler, you're typically at about 900 degrees. So from here to here, you drop the temperature to about 900 degrees C. And now you're cold enough that you can start to put heat exchangers in the flow. So 900 degrees C is still pretty hot, but you can put water-laden heat exchangers in here. So you have a series of heat exchangers that this goes through. The first ones generate steam, so if they generate steam, they're called superheaters. That means that they actually are fed steam and they get the steam superheated, so it's above its boiling point. We'll talk later this week and next week about nuclear power plants, but one of their features is they never superheat the steam. But in coal-fired power plants they do. So they'll heat the steam up to about 600 degrees C. Anybody know what the critical temperature of steam is? Of water? You remember that number? So it's about 370 degrees C. This is well above the critical point for a supercritical temperature, but it's not necessarily above the critical pressure. This particular boiler is not above the critical pressure, but some of them are. So you superheat the steam as you come through here, and then the gas is cooling down, of course, as the heat is being absorbed. And when you go down through here, you go through more superheaters and eventually an economizer, things that are heating up water now instead of steam. And the coal particles, these are just fly ash particles now, and they're just cooling down. And by the time they get to here, they're down to maybe 200 or 300 degrees C. And now they're coming out, and you go through a kind of heat exchanger that's pretty amazing. And I don't think you ever talked about it in the heat exchanger class. So this is a so now you have heat still in this flue gas. You want to get into the air that's coming in. So the air is coming through here, and you have this big air heater. And the way this air heater works is it has cages full of metal and sometimes rocks, and it just rotates these slowly on a big disc. And so they rotate in here, and this hot gas goes through these metal and rocks, and then it rotates from there into this, and air is coming this way, and the cold air goes through those hot rocks and metal, and that's the way they do this. So it's kind of a direct contact heat exchanger where you heat up something solid, and then you use that solid thing to heat up this other gas, and this just rotates on it. And those are seldom discussed, but fairly common heat exchangers. So now you've got it about as cold as it's going to go, and it goes from here, it goes out to pollutant control devices and other things. We'll talk more about those later. So that's the coal path through here. The next thing we want to look at is the air. So the fans that get used for air, so these ones, this is just the ducting for the fan. The primary fan that gets used to blow air through this boiler can be as tall as this building. These are enormous fans, and they move more air. By mass, there's 10 times as much air going through this system as there is coal. So we talked about how many tons of coal we're pushing through this system. 10 times that much air. And of course, air is much less dense than coal, so think of the volumetric flow rate of air going through this power plant. So it's like it sucks all the air out of the county and puts it through the power plant. It's not true. It's a lot more air in the county than we think. But the amount of air going through a power plant is a mind-boggling quantity of gas. So the air gets pulled in so it comes in, goes up through the air heater that we just talked about. It warms up there as it goes through the air heater, and then a fraction of it gets split off and goes through these pulverizers to pick up the coal and transport the coal out of the pulverizers. But most of it, the great majority of it, 85% of it, goes into, finds its way to these burners. And so in the burners, and toward the center, they have the coal coming out with the air. And on the outside, they have just air coming in the outer flow of the air. And it's an amazing. So the fluid mechanics of this system are pretty fascinating. So if you were to look at a cross section, just as a burner, coal is being injected like this, and the air comes in swirled like this. And so it's swirling in this tube like this, and now what's going to happen? Think of what's the pressure like in that airstream? Where's the pressure the lowest? Right at the center, right? It's anything that's swirling in the low pressure at the center, right? So this pressure is the lowest here. But now it comes out here, and the swirl is getting bigger, which means it's swirling slower, right? Conservation of angular momentum means that the rate of swirl slows down. And then it finally gets out into here, and it just flows along like this. So pressure is really low right here. We call that low pressure because it's swirling pretty rapidly. And it's high. This is the high pressure from that air. But which way is the flow flowing? This way, okay? So which way is the flow supposed to flow? The other way, right? And so they actually do this deliberately. So what happens is the air comes out like this and creates what they call an internal recirculation zone. And it sucks, so the air splits out and then comes back and recirculates here. And it slows down those coal particles so that the coal particles stay, so you get this region right here with gases that are just circulating like this. And the coal particles get in there, and that's how they stabilize the flame in front of the burner. So you slow down the coal particles, they get into that recirculation zone, and they burn in that recirculation zone mostly. That's where they ignite anyway. And so you get a nice, stable flame that sits right out in front of this burner instead of it going. If you didn't circulate this air like this, the coal would just go sail right across the boiler and smack into the wall on the other side, and that would not be. Then it would dribble down the wall and out the bottom, and that would be really bad.
So they know this effect.
Yeah, this
They're
is
mapping it.
carefully designed and very sloppily operated. But so there's a lot of technology that goes into these things, and the amount of swirl that you put in here, you can make this flame longer or shorter depending on how much you swirl this. And as you make this flame longer, it tends to produce less NOx, and shorter it produces more NOx. It's mixing more rapidly and you get a lot more oxygen in there. So a lot of the ways that they do pollution control is adjusting the amount of swirl here, trying to minimize the NOx without creating other problems. If you reduce the swirl to nothing, the flame becomes unstable. And think about this, you're putting hundreds of tons of pulverized fuel in there, and if the flame goes out and then reignites, you have an explosion, which is bad. So the whole building, think of a 30-story building erupting. That almost never happens with coal-fired power plants. It happens with black liquor plants still 1 or 2 times a year somewhere in the world. So, all right, so the air comes in through the burners, and then the air exits with the fuel, and it just goes out through the same process as the fuel did. So the next thing we need is water. Okay, so water starts off up here. The water first comes into the system through the economizer, where it gets warmed up by the hot gases coming down through here. So it gets warmed up. It's at high pressure, typically 200 to 250 bar. That's 200 bars below the critical pressure of water is about 220 some bar. So at 200 it's just subcritical, at 250 it's supercritical. So it comes in at very high pressure in very large quantities of water. It's warmed up but not boiled, and then comes down into these what they call water walls, which are these tubes that I mentioned. So these are just high pressure tubes that are welded together and form the walls of this boiler. And the water goes up the side of the walls of the boiler. And as it goes up here, it gets heated and heated, and usually designed so that by the time it gets to the top of the boiler, it's starting to form steam, saturated steam. So then it goes to a steam drum where it separates the water from the steam, and then the steam is injected through the superheaters to be superheated, so they're no longer saturated, they'll be superheated. And it will go through, and typically, because even though this is low temperature compared to here, this is still a really hostile environment here. So typically the first superheater it sees is not the hottest superheater because they want to keep the metal, protect the metal that's at the hottest that's back here, usually a little bit colder temperatures up there. And then it goes to the turbine as superheated steam and it makes electricity, and we'll talk about how the turbine works in a minute. Then it comes back from the turbine as water. Now, the turbines are actually split into several pressures, so unlike what you're used to thinking of as a turbine perhaps, you go just partway through the turbine and then they take everything back out and they put it back in the boiler again. So it comes back from the turbine and gets reheated again. So as it goes through the first stage of the turbine, it cools off and the pressure drops, but then they can put heat back into the steam again and reheat it. And so that's what they call a reheater as opposed to a superheater. So that's still superheating steam, but comes back at a lower pressure from the turbine. And that might happen in a typical power plant. That happens once or twice. That is, you put the steam through the turbine, you take it out, put it back into the boiler, put it again through another portion of the turbine, take it back out again, put it back through the boiler, and then you put it through the last section of the turbine. So it goes through, so pretty complex turbines. So that's the basis of in this case, a 450 megawatt electrical power, coal-fired power plant. The largest coal-fired power plants are twice this size. They're about a gigawatt. The ones here in Utah are about 900 megawatts. The ones in Delta, the ones that are in Hunter and Huntington, out in central Utah are smaller than that. There's about 600 or 700 megawatts. At Delta, they have two 900 megawatt power plants. So 1,800 megawatts of power being generated in Little Delta.
So those are relatively new power plants, correct?
As power plants go, that's right. They're about 23 years old. So,
Okay.
but the average power plant is about 45 years old.
Okay.
So they're probably still being paid for. They're probably about to come off the books in terms of their investment. All right, so there's just a few other pictures of coal-fired boilers. Some of the coal-fired boilers, particularly those in Europe, instead of being built so the one that I just showed you is kind of built and it gets bent over and comes down like this. Sometimes they call them tower boilers. They just keep going higher and higher. Usually if space is a concern. So there are other ways of burning coal. These ones are, from a technical standpoint, this is probably the best way to burn coal, but it's terrible from a pollution standpoint. So, but from a combustion standpoint, it's pretty easy. Here you create a cyclone boiler. You put the fuel in here, it's just circulating like this. This is kind of the size of a burner, and the fuel embeds on the side. And it gets so hot in here, so that whole flame is now contained inside of this small space. And it gets so hot, it just melts all of the inorganic ash material, turns it into a molten ash. And you have a river of slag, bright yellow slag running out of this, and runs down to the bottom of the water and drops into a big pool of water where it cools down and then pull it back out again. So along the Mississippi River Valley and the Ohio River Valley, they have several of these, but quite a few of these, but I don't think we'll ever build it. So they have very high NOx emissions and other pollutant problems. Circulating fluid beds, so this is a different technology, so we don't talk about fluid beds as much as we probably should in chemical engineering. They're used a lot for a lot of different chemical engineering applications. And in these cases, you basically fill this thing up with sand, to about here with sand, and then you blow air up through the sand, and you put fuel in there, and the fuel and the sand percolate through there, get carried up through here, and you separate the sand from the gas, and the gas goes through here, does the superheating, and there's sand circulating back around like this. For small scale applications, and for biomass applications, these are real common. So if we look at power plant efficiency, so those are just some of the technologies we use. Look at power plant efficiency based on age. You can see this trend. So the efficiencies have been getting considerably higher in terms of more recent power plants. They were quite a bit lower earlier. They went through a little bit of a surge here. This is where they started developing supercritical power plants. And supercritical power plants can be more efficient than subcritical power plants, but they're also considerably more difficult to operate. And that increase in efficiency, people decided that's not worth nearly as much, not worth the headache of operating these power plants. So they converted a lot of supercritical power plants back to subcritical power plants. In these days, this was 20 years ago, nobody was too worried about climate change 20 years ago. Now all of a sudden the efficiency became much more important, so now they've been ramping the efficiency up quite significantly on these power plants. But still, the very best power plant is maybe 38% efficient. And more typically, they're 36 to 37% efficient, even the newest ones. If you look at their age, so these are the ages of natural gas combined cycle turbines, so they're all fairly young. The gray bar here is coal. You can see coal-fired power plants are pretty old, some of them over 60 years old, and the nuclear plants are also pretty old, but they're young compared to coal, but they're old compared to natural gas plants. So there's been a big, most of the fleet has aged quite a bit. So this just shows SOx. So again, as the power plants get younger, the SOx emissions and NOx emissions and everything have come down a lot, mostly in compliance with regulation. So any questions about? So that's the way 90% of the coal is consumed in the United States in one of those power plants. Any questions about any of that before we talk about ideas for the rest of the coal?
What was the purpose of the sand in the fluidized bed?
So in the fluidized bed, the coal will react at lower temperatures than it has, but it's not stable. If you try to run what they call a suspension-fired system like the one I described, at low temperatures, it's unstable. The flame kind of comes in and out, and that's not good from a safety or equipment standpoint. So by putting the sand in there, the sand holds the temperatures, and then you can put big chunks of fuel into the sand. You don't have to pulverize it. And by pulverizing coal is hard, but not all that hard. But think about it. So if you hit a coal piece with a hammer, it kind of breaks into a bunch of pieces. But if you take a chunk of wood, for example, and hit it with a hammer, you can't pulverize biomass very effectively. You just can't pulverize biomass. So some fuels you just can't pulverize. So you put them as large pieces of fuel into the sand, and the sand stabilizes the temperature so that you put relatively cold and wet fuel in there, and the sand will keep everything hot until the fuel ignites, and then it will warm the sand back up again. And you can operate the whole thing at lower temperature and more stably by putting the sand in. Okay, so this is one way I like to think about this. So if you use, well, let me first talk about your homework, and we'll just talk about gas efficiency. In your homework, I've given you, how much time have you spent with process flow diagrams? So chemical engineers live and breathe process flow diagrams, all right? So in your homework, you have a few process flow diagrams and some statistics from actual operating power plants. And I just asked you a bunch of questions about where is all the energy, the energy that the power plant uses. Do we use it on pulverizers or fans or pumping water around? Where is the energy going? Parasitic losses, we call that. Also, you go through this diagram. So you have a diagram that, I don't know if you can all see this. You have a few of these that identify streams. They're followed by stream tables, which tell you all of the properties of those streams, what's happening in all those streams, and how things are changing. Stream tables can go on forever, but you only have 2 pages of stream tables. And then a little bit more detailed diagram of the coal-fired power plant, and then one of the turbine. In this case, it's a 3-stage turbine, an intermediate stage, high pressure, intermediate pressure, and low pressure stage of the turbine. And it shows just the properties of the turbine everywhere. Then it just asks you a bunch of questions that more or less just involve reading the diagrams, tracing things through the diagrams, and seeing how the power plant operates. So I don't know if there's anything in it. going to be too difficult. One of the things to recognize, though, is that the high pressure turbine generates a lot of electricity, but it's very small. So, so the difference, one of the things you'll calculate is the difference in diameter between the high pressure turbine and the low pressure turbine. And you'll see, and it's actually the inlet of the low pressure turbine, I think, should have been calculated. The outlet is much bigger still. And I don't think I asked you this, so I guess I should mention this. So at the end of the steam turbine, you go all the way through the turbine, and at the end of the turbine, you're cooling the steam down with cooling water. The cooling water, depending on where you're located, could be as low as 5 degrees Celsius if you're next to an ocean and you can bring cold ocean water in, and as high as 40 degrees Celsius if you're in Alabama, for example, away from the ocean, in the northern part of Alabama. There just isn't any cold water down there. Everything's warm. Everything's quite warm. And so, but in both of those cases, the pressure, so it's just steam that's in that thing. So the pressure of the steam at the point that it comes out of the lowest pressure turbine is going to be just slightly above, well, it'll be its vapor pressure at the temperature of that system. The temperature of the system is maybe 5 degrees above the steam temperature, or maybe equal to the cooling water temperature, or maybe equal to that. So recognize that these steam turbines then at the tail end, at the front end they're 200, maybe 250 bar pressure. At the back end they're at quite significant vacuum. So because the vapor pressure of water doesn't get to 1 atmosphere until you're at 100 degrees, right? So even at 40 degrees you're at a fraction of an atmosphere, and at 5 degrees a much smaller fraction of an atmosphere in terms of the pressure. And part of what you have to do is build a system that can operate at that low pressure without air leaking into it. Getting air into the steam causes serious corrosion problems all the way through the boiler. So it goes from very high pressure to quite low pressure, and the pressure ratio is much larger than 250 because of the low pressure inlet on the pressure system. All right, so what else could you do with coal? Any questions about it? Feel like you're ready for your homework? So get used to these. If you haven't spent much time with these kinds of flow diagrams and stream tables, this is a big part of chemical engineering is interpreting them. And these are very simplified ones, so the actual ones that you use will be, well, sometimes you use simple ones like this, but there will be a version of them that has every pipe and every fitting and every device on the flow diagram. And those can get pretty complex, so they're pretty hard to sort out. You can't tell what's going on there because there's just too many lines on it, too many things going on. So one cardinal rule of process flow diagrams is that the size of the device that is written on the diagram does not correspond in any meaningful way in terms of the difficulty of what it's doing. So something that's virtually impossibly difficult will be just a little box, and it will say hot gas cleanup or something like that. And something that's very simple will be the same size box with a similar kind of a label. So you'll spend almost all your time in one of those boxes, and the other ones are trivial. So aside from, coal, so let's talk a minute about coal. Where did coal come from? So coal is the remains of animals that lived on this planet millions and millions of years ago. And coal scientists can, from a piece of coal, they can look at a piece of coal and they can unlock the history of that part of the planet over the millions of years that coal formed. Looking at the coal, they can tell you about the climate, about the types of animals and plants that live there. They can tell you all kinds of things about it. It's just fascinating. You can see, still in the coal, you can still see the structure of a lot of the things, the cellular structure. In the case of lignites, you can still see cellular structures in other coals. The cells are kind of disintegrated, and you can still get a great idea of what's going on. And engineers, with their typical insensitivity to social and academic things, just dig it up and burn it, right? But you could do some much more interesting things with coal. So if instead of burning it, if you just dig it up, and so you burn it and turn it into CO2, all you're using then is the heat that comes from the fuel. But you can use, and China does use, the coal as a primary source of hydrocarbons for the whole petrochemical industry. So, they have more coal and use more coal than petroleum, actually. And it's coal that feeds their chemical processing plants and everything else. In the United States, we use natural gas in oil to feed those same systems, but in China they use coal. But you can't burn coal to CO2 and use it that way. So what you do with it is you heat it up and you generate carbon monoxide, typically in hydrogen from the fuel, and then you recombine the carbon monoxide and hydrogen, and from that you can make ethylene and polypropylene and all the feedstocks that you need from chemicals, and make this as a basis of a chemical plant. And so that process of converting coal to those light gases, carbon monoxide and hydrogen, is called gasification. So gasification has a long history. Gasification actually started during World War II. They learned to gasify coal and turn coal into diesel because there was an embargo. They, meaning the Germans, the Germans were embargoed. They couldn't import. They didn't have petroleum reserves in Germany, and the Navy had effectively barricaded all the shipping ports, so they couldn't get petroleum. So the only way they could feed their war machine was learn to turn coal into something like diesel, so that they could run their tank on coal. And that was the origin of the so-called Fischer-Tropsch process, which gasifies coal, turns it into carbon monoxide and hydrogen, turns the carbon monoxide and hydrogen into alkane hydrocarbons that still get used, and they've been used in South Africa. Always it seems like gasification has a kind of a nasty story associated with it. So it was the Germans in World War II during apartheid in South Africa. The world wouldn't sell oil to South Africa, so they actually became the experts in Fischer-Tropsch, improved it fairly significantly. Fischer-Tropsch and gasification in general have that kind of a history. But these, it's just kind of interesting to look at the research papers. These are research papers that talk about gasification. So in the previous oil crisis that we had in the early 80s, there was a big interest in gasification because everybody thought that we were going to run out of oil. And so we're going to use coal as our oil feedstock. And then oil got cheap again, and interest in gasification dropped out. And then about a decade ago, interest in gasification picked back up again because if you gasify coal, you can use it like natural gas. And potentially could use coal gasification plus a gas turbine to make a combined cycle kind of a plant. They call an IGCC plant, integrated gasification combined cycle plant. And that would be one way to increase the efficiency of a coal-fired power plant fairly significantly. So the interest in coal in gasification increased fairly significantly. Both biomass and coal increased a little bit, biomass increased quite a bit. But gasification is a pretty tough technology, and some people would look at this and say, all of the people that were active engineers here retired about here, and a whole new generation of engineers had to learn why we don't do gasification. So there's kind of a cynical way you can look at it in the middle.
Isn't Dr. Fletcher an expert in coal gasification?
Dr. Fletcher does a lot of work on gasification. The Fischer-Tropsch portion of it, you probably don't know, but Dr. Bartholomew, who retired a few years ago, is known all over the world as an expert in Fischer-Tropsch. He's probably the most renowned person in the world in Fischer-Tropsch gasification. Did any of you have Dr. Hecker? He worked in gasification as well. Dr. Fletcher does work in gasification. Dr. Lignell does gasification modeling. So it's supported a lot of research. So up through 1995, this is where most of the people were doing the research, mostly in the United States. Things changed dramatically. Since 1995, you see that the United States is still involved in gasification, but China, given their infrastructure, they have increased the amount of gasification significantly. So we have time to talk about one gasifier, and then we'll pick this up next time. This is the original kind of gasifier that people use. So gasification has to happen at pressure to make it effective, at least with coal. So you have to have a pressure vessel, and getting to feed coal into a pressure vessel is a hard thing to do. So feeding a liquid into a pressure vessel is not so difficult, but feeding a solid into a pressure vessel is tough. So you feed coal through here, you go through what's called a lock hopper, where the coal drops into a small chamber, and you seal it and pressurize the chamber, and then the bottom of the chamber opens, and it's now pressurized and goes into the pressure vessel, and you just keep doing that, kind of like the pressured vessels that you get on and off submarines through. And it falls down here, they call this a slowly moving, or some people call it just a fixed bed reactor, where the coal burns as it goes through here. If you inject water, actually water helps it degasify. And as it burns out, it comes down here, finally it turns into ash. And you take the ash back out through another log hopper. And the hot gases, you take through here and cool them down, and you send that off to turn into a Fischer-Tropsch feedstock. I'll show you just one of, so this is the much more recent and much more effective way of doing gasification now. Texaco actually developed this. The GE bought the patent from them, so now called the GE gasifier. And in this case, to get around the pressure issue, you actually mix the coal with water and pressurize it as a slurry and inject it as a slurry. So it's much easier to inject. You inject oxygen, almost pure oxygen with it. So remember the temperatures we calculated were for air with coal. If you do oxygen with coal, the temperatures get much, much higher still. So this is a very hot flame. The ceramic lined reactor melts all the ash, and the ash comes dribbling down through here. And you pull the ash out, and it's slag fines, and it's water fines, and the gases come down, and we go off. This is the steam, so you're making steam to make power. The gases go out here and produce what they call a synthetic gas, or syngas is what it's almost always called. And it has typically a composition of about 1/4 hydrogen, about 1/4 carbon monoxide, and the rest of it is water and CO2.
Yeah, so like, how efficient is the process of converting coal, gasifying it, and with, hydrocarbon to Fischer-Tropsch? In terms of carbon content, how much of that carbon do you use from?
So on paper, if you could do this the way that it's diagrammed here, you could turn, if you do a gasification with a gas turbine that burns the gases, you could make a power plant that's 60% efficient. But in order to make it 60% efficient, you've got to learn to do this particle separation from the gases while it's still hot. So you take these hot gases and you filter all the particles out to the level that the turbine would tolerate what's coming into the turbine. And you need to do that at high temperature. And the Department of Energy and a bunch of other people have spent, I'm sure, well over $2 billion trying to figure out how to do that. And at this point, I think people are ready to say hot gas filtration, that's what that process was called. Nobody knows how to do hot gas filtration. It's just probably not going to happen. And if you don't do hot gas filtration, then the efficiency of the system is about the same as a modern pulverized coal-fired power plant. And so there's still reasons that you might want to build it, because you can not only make electrical power, but you can use that same feedstock to make chemicals or fuels or other things. And so gasification still has a role. But the argument that it's more efficient really only works on paper. In practice, it's really not any more efficient, and it's considerably. This is a pressure vessel, and keeping any pressure vessel operating is much more difficult than a non-pressurized vessel. So it's a really difficult thing to. As a consequence, in the United States, we have 2 operating gasifiers. They were going to build a 3rd one, but the CEO got fired for that decision. So, of a power plant in eastern United States. But in China, there are probably 60 operating gasifiers. But they need them there because they don't have the option of natural gas or petroleum to feed the chemical feedstock industry. So most of the technology was developed in the United States and was operationally optimized in China. The Chinese know considerably more than we do about on-the-ground behavior of gasifiers. Another quick question?
Yeah, really quick. I know that the Nazis in World War II used Fischer-Tropsch to make solid aviation fuel. Do you know if that aviation fuel, if they use coal specifically to make?
Yeah, so they used coal, mostly coal, to do that.
Okay.
And that was for planes that didn't fly very high, because they didn't fly very high in World War II. You can still make, there's a city in China called Fuel City, I think. Sin, S-Y-N.
Right.
They built an entire city around one of these Fischer-Tropsch processes in northern China, just on the border of Mongolia, Inner Mongolia, and they make very large quantities of transportation fuel, which can process is higher quality than normal diesel, so you can use it for diesel for automobiles, or you can use it for jet fuel, refining it a little bit. And that's done routinely now, mostly in China.
Well, thank you.
All right, we'll pick up the application.